Hi there, so this video is wrapping up section 2.5. We're going through the last couple examples here. So we talked about in class how sine of y equals to x. We can't just use our normal differentiation rules to find the derivative because the y is inside the sine, like sine is being evaluated at y, where the output is x. Okay, so this statement actually represents inverse sine. So the equivalent statement would be y equals to arc sine of x, if you remember when we studied the inverse trig functions last year, where the domain would be -1 to 1, which is the range of sine. And then if you remember when we restricted the domain of sine to make it a 1-to-1 function, we restricted the domain to be between -pi/2 and pi/2. So that means the range of arc sine, the outputs of arc sine, would have to be between -pi/2 and pi/2. So in order to find dy over dx for this equation, I'm going to show that we are differentiating each side of the equation with respect to x. Okay, thinking chain rule, derivative of sine would be negative cosine. Not negative cosine, it would be positive cosine. Would be cosine. Leave the inside alone, and then times the derivative of y with respect to x, which is times the derivative. To finish chain rule would be dy over dx, and the derivative of x with respect to x is dx over dx, or just 1. So then it's easy to isolate dy over dx, would be 1 over cosine of y. Okay. Which is kind of inconvenient because that means in order to find dy over dx, you would need the y value so that the output of arc sine, the y-coordinate of points that lie on the graph of arc sine. And it's easier whenever we have dy over dx in terms of x, or even in terms of x and y. And we actually can think about writing this particular derivative in terms of x. If you remember last year, whenever we thought about rewriting trig expressions in their equivalent forms in terms of x, we used either like right triangles, or we used the trig identities. So like one trig identity or one relationship we know between sine of y and cosine of y would be the Pythagorean identity, saying sine squared of y plus cosine squared of y is equal to 1. Where then, if we try and solve for cosine of y, because we're trying to figure out how we could potentially replace cosine of y in terms of x. So then we could say, okay, well, cosine squared y would be equal to 1 minus sine squared. So cosine of y would be plus or minus the square root of 1 minus sine squared of y. Well, then we think, okay, well, cosine of y on the interval from -pi/2 to pi/2 for y. Looking at this interval again. On that interval, cosine would only be positive, because remember that interval covers quadrant 1 and quadrant 4 of the unit circle. The negative angles being from quadrant 4 or terminating in quadrant 4, and the positive angles terminating in quadrant 1. So this statement is actually only true for the positive square root of 1 minus sine squared of y. Okay. We also know what sine of y is, right? Sine of y we were given is equal to x. So we can make this statement, right? So since sine of y is equal to x, we can replace sine of y and say that cosine of y is equal to the positive square root of 1 minus x squared. So this derivative could also be written as 1 over the square root of 1 minus x squared, which can be helpful, and this is kind of getting ahead of where we are. Currently, I need you to be able to really understand how we got to the derivative of this equation, sine of y equals to x, being equal to 1 over cosine of y, and we will end up revisiting the derivatives of the inverse trig functions soon. So this question is, find the largest interval of the form negative a to a on which y is differentiable function of x, on which y is a differentiable function of x. Well, looking at our derivative here, we want to find interval of y. So if we look at the range of arc sine, well, the range of arc sine is between negative pi over 2 and pi over 2, right? Like, so the inputs here would be between negative pi over 2 and pi over 2. Well, if we were to think about inputting negative pi over 2 or pi over 2 into cosine, that would be 0, and we'd end up with 1 over 0, so vertical tangent line. So the equation is technically not differentiable at the endpoints, negative pi over 2 and pi over 2, but it would be differentiable over the rest of the interval because the rest of the graph is of sine of y equals to x is smooth and continuous. So it would actually just be from negative pi over 2 to pi over 2. Okay, if we are thinking about inverse sine. Okay, and then our last example here, we're just getting some extra implicit differentiation practice because we are actually going to find the second derivative. Okay, so this notation represents the second derivative, and the way that you could think about it is that if we have dy over dx, for this notation I mean, so if we think about having dy over dx, and then the second derivative is the derivative of that, so using the notation to indicate that we're taking the derivative of the derivative, that would end up being this d squared y over, and I know parentheses aren't used, but this is the notation that we use for the second derivative in the Leibniz, I always say wrong, sorry you guys, Leibniz notation. But to find the second derivative, we need to figure out what the first derivative is. So let's think about differentiating each side of this equation or each term. So showing, this is the step where we are indicating what we are differentiating with respect to, because we're not always necessarily differentiating with respect to x. Okay, so derivative of x squared with respect to x would be 2x, and then derivative of y squared with respect to x, we would think chain rule, so that will be 2y times dy over dx, right? Because derivative of the outside, leave the inside alone, times the derivative of y with respect to x would be the dy over dx. And the derivative of the constant would just be 0. So then we can isolate dy over dx. And if we subtract by 2x on each side, and then divide by negative 2y, we will end up with x over y for the first derivative. I'll use a different color here. So then when we want to find the derivative of our first derivative, which will give us our second derivative, and I'm using implicit differentiation again because dy over dx is in terms of x and y. Okay, so then derivative of y with, derivative of dy over dx with respect to x, well, that is our second derivative. And then we need to think quotient rule for derivative of x over y. So low d high would be 1 minus high, and d low, so the derivative of y with respect to x is dy over dx. We were able to put 1 for the derivative of x with respect to x. All over low, low. So to clean that up a little bit, that's y minus x dy over dx over y squared. Now here's the thing, we could leave as is, but we know what dy over dx is equal to, right? We know dy over dx is equal to x over y. So we can replace dy over dx with x over y. And then we have a complex fraction that we're going to want to get rid of. So we can multiply by y over y to get rid of the complex fraction. So our second derivative will end up being y squared minus x squared over y cubed. Okay, and if you're recognizing the fact that you could go a step further, if this would maybe come up as like a multiple choice, if you're looking and you're like, wait, this answer is not there, you could go back and say, x squared minus y squared equals to 16. Well, if we do some rearranging there, so if we were to maybe factor out or multiply by -1 on each side of that equation to turn it into y squared minus x squared equals to -16, then you could say, we could actually replace the numerator there with -16. Just could potentially be something, a thought you have to have in order to get a multiple choice answer. Okay, so then that would be our second derivative.